Welcome back. In this video, we're going to finish up our discussion of least squares and how it gives rise, this type of problem gives rise to multivariable functions that are extremely valuable from the standpoint of the theory of this calculus class. Recall from the last video that we had talked about a collection of data points, t sub 1, y sub 1, t sub 2, y sub 2, etc., that roughly could be modeled by a line. And the whole idea was that we were going to construct individual error functions which were given by the difference between the modeled value and the actual collected value. And we call that, for the ith data point, we call that e sub I. And notice that these are all a function of m and b. This is a multivariable function. Depending on the y-intercept and the slope that I choose, each individual error is going to be different. Here we call this y sub I minus the output value of the function, which was m times the collected input value plus whatever the y-intercept was. Okay. A few things to notice here. This function comes directly from the data, so these two things here are given in black. This was given by the data, which meant somebody paid a lot of money for some other person to collect the data. And then this was given as the independent variable. And these two parameters were unknown, aka the mathematician that is paid to create this model, actually statistician probably, would want to determine these based on the actual behavior of the data. The main idea of least squares is to find values of m and b so that the model optimally fits the data. Do you recognize this word optimal from the standpoint of calculus? Optimize the model. In calculus 1a, when we optimized a function, we try to find the min or the max. If we wanted to find m and b to optimize something, what would we optimize? Perhaps the errors. And would we want to minimize the errors or maximize the errors if the model was valid? Yep, you got it. Minimize the total error, aka minimize error. I want to make a quick announcement before we go on about this error function. Note, e sub I can be positive if the modeled output is bigger than if the collected output is bigger than the model output, which is the case here, right? The collected output lies above this, so this error right here is a positive number because we're subtracting the modeled away from the other one. But it can also be negative. And this happens when the collected data lies below the modeled data, which is exactly what's happened here, right? The collected data point lies below this one, meaning this error is a negative. And we'll talk about why that's kind of an important observation in a bit. Okay, so the whole idea is we have this data, we want to find parameters to optimally fit the model to the data. The question is, when we go to optimize something in calculus, we need a function to actually optimize. So we need to create a function, multivariable, to optimize. So let's start with the first idea. Just the sum of all the errors. Sum the individual errors. Okay, so we might think that one total error function that we might try is just to take all of these individual errors and sum them together. And of course, this would be a function of m and b since each of the individual errors is m and b. So here we've got one. There were 14 different data points. And then we're just going to go ahead and sum each of these individually. Okay, so now we've got this. I goes from 1 to 14. Y sub I minus m t sub I. I guess minus b is okay. Just distribute the negative there. Okay, this is an idea except that it has a major flaw. This error, this total error function, could produce nonsense. In particular, when we go to minimize this, imagine we had a data set that looks like this. So you have maybe one here, one here, one here, one here. And you say to yourself, well, it really should be something that looks like this. It should be increasing linearly. So the model that I want should be increasing linearly. But when we look at this total error function, because each individual error could be negative or positive, you could have a situation where you have a complete nonsense model, but the total error measured by this function is 0, because the negative error cancels out the positive error, this negative error cancels out this positive error, and even though the data trends upward, this error function doesn't show that because some errors take away from others. So, unfortunately, this one doesn't work, but it's a step in the right direction in the sense that we're trying to minimize somehow counting all the total errors. Okay, the problem with this error function was that some were negative, some were positive. How might we fix that problem? Yep, you got it. You might try to turn all errors to positives. So let's try idea 2. Do you know any functions that turn negatives to positives and leaves positives alone? Yeah. Absolute values. Okay, so I'm going to call this the 1 function. And this is related to 1 norms, which are absolutely beautiful. You don't have to worry about anything I just said. So here there's 14 data points. And instead of taking the sum of the individual errors, we'll take the sum of the absolute value of those errors. Okay. This thing is a very, very beautiful function in the sense that we're now looking to minimize the absolute value of the difference between the collected data point and the model data point. One of the questions that we would have is how do we minimize this function? And this is where we would run into a lot of pain and suffering, or what mathematicians like to say, a career in research. This function, while it is a really, really good function, is hard to minimize. In particular, do you remember anything about absolute values? what is the derivative? When you go to minimize something, you try to take the first or second derivative test, right? What do you know about the derivative of absolute values? So when you look at an absolute value, it's like a mighty duck flying V, right? Here we go. The flying V. All right. The derivative right there does not exist. And if you want to minimize this thing using calculus, you have to find where the derivative doesn't exist. Look on the left-hand side, look on the right-hand side. This is going to be a beast of a problem. These things suck. Right? So when you go to try to minimize this with respect to M and B using calculus, we're up a creek without a paddle. So even though this particular idea of the total error functions with respect to the absolute value does solve the problem of making sure all the errors are measured as non-negative numbers, it doesn't solve the problem of allowing us to do this before our kids graduate from college, right? This is a hard problem. So then we ask ourselves, well, is there another type of function that we could use that guarantees positivity and behaves really, really well when it comes to derivatives? Yep. So this is going to be idea 3. Take the total squared error. And we're going to call this the total squared error, which is a 2. Okay. Instead of summing the individual errors or the absolute value of the errors, we're going to sum the errors squared. Here this is M and B. Okay, so now we go 14 data points. Here's y sub y minus t sub I. And here we have M and B. And I guess I'll just go ahead and distribute that right out. All right. So now our goal is to use calculus to minimize this function. In particular, we're going to construct the second partial derivative test, which allows us to minimize multivariable functions using this idea of derivatives in multiple variables. And this will allow us to produce the optimal M and B that best fit this. What's really nice about this square is it turns all errors into non-negative numbers, and it behaves really, really well from the standpoint of calculus. There is a third reason why we use this square, and it has to do with something called a Hilbert space or an inner product space. Later in your career, you're going to see this square not only as a calculus problem, but also as a matrix or vector problem. And you'll see that there's a really, really functional way in linear algebra to avoid having to do calculus. However, locally what we've just seen is a way to translate collected data into a multivariable function to which we can apply calculus that has a very, very powerful meaning. The solution to this minimalization problem that comes from calculus will produce the parameters M and B that give us the line of best fit, the line that minimizes the total squared error between the modeled data points and the collected data points. This is amazing, isn't it? I also want you to notice this is the beauty and the pain of applied math. Never in life where you're going to be given some function that's valuable to you that you can just apply the theory in this class. More often, you're going to have to work really, really hard to translate stuff in your life into a mathematical notation, which then you can use the theory of this class to analyze. We'll talk more about this as the quarter goes on. For now, I'll see you in the next video.